Hello, so we're going to continue with part 2, chapter 5, thermal chemistry. Just to remind you that the step-by-step answers are on the Blackboard site, Common SEC 201 account. So we'll continue with calorimetry, Q equals ms delta T. Here the question is a piece of metal weighing 49.047 grams was heated to 100 degrees Celsius and then put into 100 milliliter of water, initial temperature of 22.3. You put the metal in the water, it was allowed to go to equilibrium and a final temperature of 27.8, and they're asking for the specific heat of the metal. So the first step here is to find the heat for the water. So you use Q equals ms delta T. We have for the water, let's say for the water, for H2O. And once we have this information, we know the heat that's gained for the water will be coming from the metal. So you have a hot piece of metal, you put it in the water will gain some heat, and the metal will lose some heat. So the heat gained from the water comes from the metal. So first thing, we need to find the heat for the water. We know the mass of the water because we know the density. If the volume of water is 100 mils, we use D equals m over V to find the mass of the water. So the mass of the water will be 100 grams. 100 grams. We know the S for the water. 4.184. 4.184. And we know the temperature change. The final temperature is 27.8 and the initial temperature of the water is 22.3. So that change, we know the change of temperature. 27.8, so that would be 0.5, try 5.5. So we know all the values, we can figure out Q, and Q comes out to 2301.2 joules. This is the heat transfer to the water. So again, we use this so we can find the S for the metal. So for the metal, we don't know the S. We know Q, which is negative 2301. We know the change in temperature. Let's write this down. T2 equals to 27.8. And T1 is going to be 100 degrees. That's how much the metal was at the beginning. So this will come out to a negative value as well. So we plug in the values. Q equals, well, let's write out the equation for you. M is 49.047. Change in temperature, 27.8 minus 100. Q is now negative. When we work this out, our S comes out to be 0.64. And the unit, joule per gram Celsius. Okay, so multiple steps here using Q equals ms delta T on 2 occasions. Once to find out the water, how much is absorbed by the water, and work backwards to find out the S for the metal. And the S's for, in general, for metals should be less than 1. Another question where we now use our limiting reactant concept. Question here is when 60 mils of 0.2 barium hydroxide and 60 mils of hydrochloric acid are combined, a strong acid and a strong base, which is an exothermic reaction, which means the change in delta H will be negative because heat is released when a strong acid and strong base comes together. So we have the equation here. The first thing we should do is check if it's balanced. Yes, it's balanced. So let's find out the Q. This is at constant pressure, so equal to H, delta H. So Q equals, or I can just say H here, just to make clear, MS delta T. We know the temperature change, 2. We know the specific heat of water. A strong acid plus a strong base gives you water. So times 4.184. And do we know the mass? Yes, it's 120 grams right here. 120 grams. So when we work this out, our Q value, or delta H, will be 1004.16, and this unit will be joules, and we convert it to kilojoules because they're asking for in kilojoules per mole. So this would be 1.004 kilojoules. Now we need to find out, the question is asking you per mole, so we have to figure out which one is the limiting reagent. And we have the information above here to figure out the moles. We use the balanced chemical equation to find BaCl. You can also use it to find H2O as well. You can pick either one to determine which one is the limiting reagent. Reagents are on the left side. So let's start with the Ba. Let's try the BaOH, barium hydroxide. So in this case we have 0.2 times 0.06 liters, have to convert it to liters. We multiply the two out, we get 0.012 moles. What is the ratio between the two? Between BaOH and BaCl2, it's a 1-to-1, so the ratio stays the same. So the moles of BaCl2, 0.012 moles of BaCl2. We do the same thing with HCl. You have the volume, you have the molarity. Multiplying the two together, you get, so for HCl, you get 0.006. What is the ratio between the two? Between here and BaCl2, it's a 1-to-2, so the 1 goes on top, the 2 goes on the bottom, the HCl's will cancel, and you're left with 0.003 moles of BaCl2. BaCl2. So when you compare the two, this one is the lower one, 0.003, meaning the limiting reagent is HCl. So the question is, how many kilojoules per mole? The answer would be 1.004 kilojoules divided by 0.003 moles of moles of BaCl2, and we get here negative 334.3 kilojoules per mole. Exothermic heat will be released when a strong acid and a strong base come together. So here we start a new topic of Hess's law. Recall that enthalpy is a state function, so therefore we're only concerned about the beginning conditions and the end conditions. Hess's law is a way where we carry it out in a step-by-step reactions. We can calculate the delta H for each step of the reaction, so how we get the intermediates, which leads to the product. So for instance, if we were to do an experiment where we had A and B, and we were not able to measure this delta H to get our products, but if we were able to measure the step-by-step process, we could find the delta H, the change in delta H for the reaction. So here's an example where we have methane plus O2 giving us CO2 plus H2O. We were not able to figure out the enthalpy change. However, we were able to calculate or determine the intermediate steps going from CH4 to 2O2, giving us CO2 and H2O gas. This value was negative 802. And then we were able to measure the final step going from CO2 gas and H2O gas to CO2 gas and H2O liquid, which is negative 88. If we add the two up, we get negative 890 kilojoules. So for this reaction, which is an exothermic reaction because of the negative value, we get negative 890 kilojoules. You can see here the waters will cancel out when we added the two equations. The waters for the gases canceled out. They will cancel out because they're both on the left side and the right side. The CO2s, these two CO2s will cancel, leaving us one CO2 here in our final answer. So continuing with Hess's law, we talked about in the previous set of slides that if we reverse a reaction, so if the products become the reactants and the reactants become products, we have to change the sign of delta H. Positive becomes negative or the negative becomes positive. If we multiply both sides by a chemical reaction, a factor of A, we must do the same to the delta H. So if we multiply the reaction by 3, we have to do the same to delta H. And we have to be cognizant of the physical states of the reactants and products. So here's an example below where we don't use particular chemical compounds. We have here 2A plus 3B gives us C plus D, etc. We have 3 sets of reactions, and we need to find out, get the overall reaction of 3A plus B to give us E. So we look at the first case here, E, the second reaction, E plus A gives you C. We notice at the very bottom here that the E is located on the product side. So what we would do is we would flip E plus A, C. So let's rewrite it out here. On the right side, C plus C gives you A plus E. So now we have E on the product side. We also have E on the product side on line number, let's call this line number 4, line number 3, line number 2, and line number 1. So we flipped equation number 2. We also see we have D here in equation 3, 0.5 on the left, and we have 1D on the right. In equation 4, we don't have any D's. So what we would have to do is multiply line 3 by 2. So let's rewrite everything out. We have 2a, rewriting this out, 2a plus 3b gives you c plus d. Line number 3, what did we do? We multiplied everything by 2, so we have 2a plus d gives you 2b. And now we want to see if things cancel out to get us our final product again. 3a plus b gives you e. We see here the c's will cancel, one on the right, one on the left. With the d's, we have one on the left, one on the right. With regards to the a, we have 4 a's on the left, and we have 1 a on the right. So that will give us our 3a. And with the b, we have 3 b's on the left, 2 b's on the right, which gives us an overall b on the left. So that's not the final answer. What we've done is we have flipped equation 2 as we reverse the 2, so we put a negative here. We also multiplied equation 3 by 2. So we multiply by 2. And when we add these 3 delta H's up, we get a value of negative 16 kilojoules. So let's give you a try. You can pause. Again, you have to manipulate equations 1, 2, and 3 so that you get an overall equation number 4 here. So equations 1, 2, and 3, just ask you to pause, and we'll come back in a second. So coming back, we see the first thing we see here is there are 2 graphites, 2 carbons here, and only 1 here. So we're going to multiply the first equation by 2. And if we multiply the equation by 2, we have to multiply the delta H, the corresponding delta H, by 2. We will also see here that we have C2H6 in the reactant, C2H6 in the product. We have 2 of them, so we have to flip. So flip this equation around and divide by 2 for equation 3. And we also observe here, because we've done that, we flipped it and divide by 2. This now becomes 6. This becomes 3 waters on the reactant side, and we have 1 water on the product side. We have to multiply this by 3 so that the waters cancel. We don't observe any waters in equation 4 here. So let's see if this works out. We have let's rewrite the equations. We have 2CO2 let me redo that. We have CO2 as a product. So in the first line, what did we do? We just multiply everything by 2. 2 graphites plus 2 O2s gives us 2 CO2s. If we look at equation 2, what did we do? We multiplied everything by 3. So 3H2 plus 1.5 O2 plus 3H2O. And for line number 3, we flipped and divided by 2, so we come up with 3 H2O plus 2 CO2 gives us 3 O2. 3.5, I'm sorry, 3.5 O2 plus C2 plus 1 C2H6. So when we start canceling out, we again want to obtain this product here, or this final line of line 4. This corresponds now with this. The 3H2 corresponds here. The C2H6 corresponds to this product. And hopefully everything else cancels out. So let's see if this works out. The 3H2Os on the left and the right. The 2 CO2s on the right and the left. And we have 3.5 O2s on the left and 3.5 O2s on the right. So everything will cancel out. So again, that's not the final step. We multiplied line equation 2 by 3. What did we do to line 3? We divided, we flipped, and we divided by 2. So when we do that to all the delta H's, we add up all 3 of the delta H's, we get negative 83 kilojoules. So let's give us another example to try. You can pause and come back when you've tried. Let's just first label our equations. 1, 2, 3, 4. The first thing I notice here is the HNO3, nitric acid, appears only in equation 2. So we have to divide equation 2 by 2 so that this comes down to 2HNO3. The second thing to realize here is the NO2 appears in the reactants. It only appears in line number 1. So what do we have to do here is we have to flip to get it onto the reactant side and multiply by 1.5 so that we get 3 NO2. So let's just write this out for you guys first. We have 3 NO2. I'm just flipping and multiplying by 1.5. Gives us 1.5 O2 plus 3 NO. What did we do to line number 2? We divided by 2, so we got N2 plus 2.5 O2 plus water gives us 2 HNO3. And now we have to worry about line number 3. Do we do anything to that? We will flip line number 3. And why would I do that? Well, because we have now N2 on the left, we have N2 also here in line number 3, so we have to move line number 3 over. So we have to flip line number 3, so we're going to flip this. We flip it over, then we get 2NO to give us N2 plus O2. So now let's just see if we got everything okay. We have the NOs here matching. We have the HNO3 matching. We have the water here matching. We have the NO. We have 3 NOs on the right and 2 on the left. So we're okay with the NOs. And with oxygen and nitrogens, the nitrogens will cancel. And the oxygens will cancel. 2.5 on the left. 1.5 plus 1 is 2.5 on the right. So those will cancel as well. So we did okay with manipulating the three equations. Again, whatever you do to the equation, you have to do to the delta H's as well. And when you add these three numbers up, when you make this one positive and multiply by 1.5, take the second one, divide by 2, negative 128. The third one, you flip, so it becomes negative 183. The first one will become 174. When you add the three up, you get negative 137. The next topic is enthalpy of formations. So here it says when you change the energy needed to form the particular compound, and we establish this with a baseline with standards, meaning these occur at 1 atmosphere and 298 Kelvin, 25 degrees Celsius. So we come up with these standard enthalpies of formation, meaning that at these conditions, we can decide how much energy is produced or released to make that particular compound. So in the delta H is the enthalpy change, F stands for formation, not final, and this circle here in the top right indicates our standard state. Standard state, again, means at 1 atmosphere and 298 Kelvin. So here's a chart of standard enthalpies of formation, which will be given to you. You can see, for instance, if I looked at something like water, right here, it's negative 285.8. What does that mean? That means when the oxygen, to make water, so when the oxygen and the hydrogen come together, it will release negative 285.8 kilojoules per mole of energy if I were to form H2O liquid. Diamonds, which has a 1.88 value, it's not 0 because we know diamonds are not formed on the surface. They're formed in the, in high pressures and high heat situations. So with the enthalpies of formation, there are some elements that at 1 atmosphere and 298 Kelvin, they have a formation, delta H, not formation of 0. Things like O2, Cl2, N2, and also some solids as well. And you'll see here aluminum, iron, solid. Those have a value of 0, and we call this a sea level, meaning that you can have things that are above sea level, which have, we can just say arbitrarily, negative values, exothermic, and we can have things below sea level, we can say endothermic. And will need energy. So in this case, we look at the question, which one of these have a standard enthalpy formation equal to 0? The Ne, which is a noble gas, standard state of 0. As I just said, solids, sodium would have a value of 0, and diatomic gases also have a value of 0 as well. How would we put this in an equation, or how would we find the delta H of a reaction? The general equation is delta H naught formation of products minus the sum of the delta H naught formation of reactants. So again, it's products minus reactants. We do have to take into account the coefficients in front. So the little a, the little b, and the little c in terms of the coefficients. But again, it's just products minus reactants. So this is an example here. We have C6H12 plus 9O2, 6CO2, and 6H2O. And the table will be given to you, but for the delta H formation of C6H12, it's negative 151.9 kilojoules per mole. So if we were to take the products minus the reactants, I've worked it out step by step. Where did I get these values from? I got them from the table that I just previously showed you. I took into account the coefficients, 1 for C6H12, 6 for CO2, 6 for the water, 6 for the CO2. O2 will be given a value of 0 in a stable form at 298 Kelvin and 1 atmosphere. And when I did the math, I get negative 3924 kilojoules per mole. So I wanted to give you guys a try. We'll pause for a second the video and then I'll give you guys a try. Here we have C2H2 plus 5O2 giving us 4 CO2 plus 2 H2O. So again, we do products minus reactants. So let's do the products first. We have here 2 H2O, or let's do it for you, 2 times negative 285. This is the value for water. We also have 4 CO2, so 4 times the CO2 value, carbon dioxide, times negative 393.5. And so that's the products minus the reactants. So it's time minus the reactants. The reactants consist of 2C2H2. So 2C2H2, 2 times 226. And O2, as I mentioned earlier, will have a value of 0. So oxygen O2 gives a value of 0. When you do the math, we have again products minus reactants. We get here for the product side minus 453. And for the reactant side, we get negative 2144. We do the math, we get negative 2597. Next one, we have calcium carbonate, gives us calcium oxide solid plus CO2 in a gaseous state. We again do products minus reactants. First, we have to make sure it's balanced. I should have said that in the previous equation. We have to make sure the equation is chemically balanced. So we have here our products. We have negative 635.5. This is for our calcium oxide. The coefficient that goes in front is a 1. The next one, we have here CO2. CO2, the value for CO2 is negative 393. So products minus the reactants. The reactant here, CaCO3. $1207.1, and when we do the math, we get 178 kilojoules per mole. So that's part A. Part B is asking you what would be the enthalpy change in kilojoules if you made 33.3 grams of CO2. So here we have to use some of our knowledge from chapter 3. We have 33.3 grams of CO2, 3 grams of CO2. We need to divide by the molar mass to get our moles. So we would divide by 44, mole goes on top. CO2 goes on top. On the bottom, we have 44 grams. We got this from the periodic table. CO2 molar mass is 44 grams. This comes out to 0.756 moles of CO2. Let's write this moles of CO2. And then we multiply out by 178 kilojoules per mole. The moles will cancel, and we're left with 134.6 kilojoules.